Hi folks, and welcome back to Physics with Captain Rod. Making this video here to be kind of a follow-up to my first video here about the beginnings, if you will, of vertical motion due to gravitational acceleration. Now, I've already done some of this work here. We're going to imagine that young Timmy here drops this basketball and it accelerates down under the influence of gravity at about 9.8 meters per second. I've chosen a coordinate system, and I talked about that in my last video. I've chosen it in such a way that the y coordinate of the ball at t equals 0 is 0. It doesn't matter what the x coordinate is because it's not changing. I could put this coordinate system left or right anywhere I want. For that matter, again, I talked about this in the last video. You can put it down here if you wish, but I'm just going to leave it right here. I talked a little bit last video about these graphs. You know, the acceleration is constant and opposite of what I'm calling positive. That's going to give me a linear velocity graph looking something like this and a position graph looking like my top one. So now what I'm going to do is talk about, well, how do we write equations for these things? So specifically, I'm going to be talking about this one and this one. So we're going to take that acceleration graph and also write this fact out. Acceleration is change in v over change in t. Now, your change in v is therefore equal to acceleration times your change in t. And a very important kind of fact of life here is what this is on the graph. In this graph, your acceleration is this, your delta t is this, and the product of the two is this area here. So that's what this thing is going to equal. Now the acceleration is constant. You can just put acceleration times time, but I think it's very important to point out that this product here on this graph is an area. So our change in v is going to be the acceleration. I'm just going to go ahead and use numbers for this, which is negative 9.8 meters per second squared. I'm going to put a little NCU here, which stands for note consistent units. So acceleration times time. Now, delta anything is always v final minus v initial. So this can be written v minus 0 equals negative 9.8 t. For my v final, I'm just going to put v here, and hopefully it's understood. That's my v, which goes along with this t. That's a function. And, you know, if we get rid of the 0 here, we get the equation for this line. v equals negative 9.8 t. Right now, we're going to move up and try to use this graph to get this function. And let me write this out for starters. Your velocity is equal to delta x, or in this case I'll say delta y over delta t. This is whatever variable you're using to track the particle. Your delta y is therefore velocity times delta t. Now remember here that your velocity is this dimension, the times this dimension, and the product of the two is this area right here. Let me do that in green because it looks so nice. So this area right here is going to give us our change in v. Now, from here to here on the graph is what we're calling t. And from here to here on the graph, that's what this is, which is equal to this. So when we calculate our change in area, that's going to be our area, not change in area, this triangular area, that's going to be 1/2 t times this negative 9.8 t. And that will clean up a little bit to minus 4.9 t squared. Now, last little step here is this. Your delta y is y final, which I'm just going to call y, minus y initial, which is 0. That's because of where I chose to put my coordinate system. Now, had we put the coordinate system down here, again, that's a common choice in problems like this, then your y initial would be whatever this height is. So that will depend slightly, or depend on how you choose your coordinates. But I'm going to go ahead and stick to the 0 that I have. Right, equals minus 4.9 t squared, and we'll just get rid of the 0 that we don't need. So y is going to equal minus 4.9 t squared. So now at this point we've gone from, you know, my first video about making sure you draw the pictures and write down important information and label everything. Next thing you do is you choose a coordinate system to work in. Next, sketch your acceleration graph, velocity graph, and position graphs relative to the coordinates that you're working in. Now, the point of this video, how to write the equations for the particles, right? So this area gives you your delta V, and that's what that fact right there is what allows you to write this equation here, yielding this basically after you clean it up. And then this area here gives you your your delta Y, allowing you to come up with this function right here for this animal. Now, some things that can change in these types of problems, perhaps Timmy throws the ball up in the air with an initial velocity. Let me talk about what would that change with all this work. This wouldn't change at all. Once that ball leaves Timmy's hand, the acceleration is down at 9.8 meters per second, doesn't change. This graph would have a positive initial velocity, and then that velocity would decrease linearly. And that will make the area calculation a little bit more intriguing. And I'll save that for another video. But conceptually, you do it the same way, area bound under the curve. It's just you end up with a little bit more complicated area. You end up with a trapezoid instead of a triangle. The other thing is perhaps Timmy throws the ball down at some initial velocity. This intercept would be down here somewhere because the initial velocity would be some negative number. And then that velocity will decrease, again yielding a trapezoidal type area. So anyway, just meant to be kind of an introductory video on how to write equations that describe falling objects or objects accelerating under due to the influence of gravity. I'll make more examples which include initial velocities. So I hope that this helps get you on track. Have a great day.